Okay, let's take another look at our simple little integrator circuit, but this time let's use the impedance of the capacitor to do the analysis instead of writing out the integration. Just as before, the current from the input into the circuit is V sub I divided by R. All of that current enters the capacitor since we assume the current into the input of the op-amp is 0. Thus, the voltage across the capacitor, positive reference on the left, is VI divided by J omega RC. Once again, this is an inverting structure, so V out, the final output voltage, is going to be minus VI over J omega RC. Now, just sort of ignoring the minus for the moment, we could deal with that if we really need to. Let's think about what happens as omega changes. As omega gets larger and larger and larger, the magnitude of V out gets smaller and smaller and smaller. And conversely, as omega gets smaller, V out gets larger. In other words, this is going to act like some sort of a crummy low-pass filter. For those of you who remember this from earlier courses, this will actually roll off at 6 decibels per octave. Each time you double the frequency, you go down 6 decibels. If you don't remember what a decibel is, go back and review that. Now, we do have one immediate problem which we foresee. As omega approaches 0, in other words, as omega heads toward DC, then the gain becomes infinite. Now, that does not mean that if you put 0.1 microvolts for your input voltage, that the output is immediately going to get huge. No, that's not what it means. Remember, we're doing an integration. Also remember, the voltage across a capacitor cannot change instantly. What this infinite gain means is that if you put a DC voltage on your input and you leave it there, then the output of the circuit is going to head off toward infinity. Positive or negative infinity, depending on what the sign of V sub I is. Now, of course, it can't do that. It can't get to infinity because, remember, for most op-amps, you can only come within a couple of volts of your power supply levels. So if we're running this on a typical plus and minus 15 volt power supply, then if you have a positive DC voltage on V sub I, it would head toward minus 13 more or less. Or if you had a negative V sub I DC component, it would head toward about plus 13 volts. Depending on what R and C are and depending on what VI is, it may take quite a while to do that because it's got to charge up the capacitor. But if you leave it there long enough, eventually you're going to hit the power supply limits. So that's a potential problem with this circuit because it's really, really difficult to guarantee that there is no DC component in your input voltage. And that's not even to mention the input bias currents, which you can come pretty close to getting rid of, but you can never make them exactly 0. You can make them very, very small, but you really can never make them exactly 0. So that's another potential problem with this circuit. Now, there are many applications where it's so small and something about the circuit changes before it has time to integrate that DC component. We'll see a simple oscillator where this is true, that it may or may not be important in a specific circuit. But if you just hook this up and leave it for a very long time, eventually you'll probably run into a problem. Our next video will discuss how to solve this problem so you don't have to worry about even minuscule little values of DC offset in V sub I or your input bias current causing your op-amp to pin itself to one of the supply levels. So you can look forward to that in the next video. Bye.